Learners. Today we are going to explore a very interesting concept in electronics, that is energy band theory. So this theory helps us to understand why some materials can conduct electricity, why some materials will resist to conduct the electricity, right? And why semiconductors are very important, and how the semiconductors stood as a backbone for the technology, modern technology nowadays. Okay, so how we'll understand how electrons behaves in solids, and what makes materials like conductors, semiconductors and insulators. We'll see the differences in conductors, semiconductors and insulators. Yeah, so in this video we'll cover the topics like what is the energy level. We'll start with the energy levels in the single atom as reviewed by Bohr's model. We'll remember how were the discrete energy levels, and by that we'll connect to the energy bands. Okay, the energy levels in the Bohr's model concept, we'll connect that energy levels as simple as possible, and we'll understand what are energy bands in solids. And then we'll learn what is a valence band and what is a conduction band, right? We'll understand the forbidden energy gap between the valence and conduction band. Next we'll also learn classification of materials. So as we know, materials are classified as conductors, semiconductors and insulators. So we'll see what makes the material a conductor, what makes it semiconductor, or what makes it insulator. And finally we'll practice some questions to test your understanding. To understand that did you understand the video or did you understand the topic of today, right? Let's get started. Now, do you remember Bohr's atomic model that we have studied earlier classes? Right. Electrons orbit the nucleus in fixed energy levels, right? As you can see here. Okay, this is a nucleus and the electrons are moving in a fixed energy levels. Fixed energy levels. The energy levels are n is equal to 1, 2, 3, 4, 5, 6, 7 and so on. Right? Like I also said you the example like the steps on the staircase. You can stand on step 1, you can jump to step 2, you can jump to step 3, step 4, but you cannot stand in between first step and second step, right? In the similar way, electrons can also exist in specific energy levels only, not in between, not in halfway. That is only called discrete levels, not a continuous level. Okay, each orbit has a fixed energy also. Electrons can jump between levels either by absorbing the energy or by releasing the energy, but we said they cannot exist between these levels. Okay, so these are the levels. N is equal to 1, 2, 3. It can jump from higher to lower level, or it can move from lower to higher levels, right? So this was about the only single atom, isolated atom, where the electrons in each orbit possess definite energy. But in the case of solids, what happens? The energy level of the outermost orbit electrons is affected by some neighboring atoms, right? By some neighboring atoms. So in crystal, or we can say in solid, you will not have only one electron or one atom, no. You will have many millions of atoms. So when two, let us take the example of two isolated charges. When they are brought close to each other, the electrons in the outermost orbit experiences an attractive force from the other nearest atoms from the nearest atoms. Okay. So due to this reason, the energies of the electrons will not be at the same level. The energy levels of the electrons are changed. can be higher value or can be lower value. So the electrons in the same orbit can exhibit different energy levels. So this grouping of energy levels, is known as energy band. It is known as energy band. Okay. Now when you imagine billions of atoms in a solid, in a crystal, right? There will be some billions of atoms, some 10 power 23 in number. So when you imagine billions of atoms coming together to form a solid, so separate energy levels begin to interact. See, separate energy levels begin to interact. They split into billions of like closely spaced energy levels. Okay, they'll merge into one another. Like here, they'll merge into one another, and what they become? They become a band called valence band here, and they become a band here called conduction band. So instead of like single few steps, we now have some bands of energies. Okay. So did you understand how the single atoms, uh, how they are distinct and how they have the separate energy levels? And when coming to many atoms, the energy levels are, they start to interact and they start to split. Okay. And we're coming to a solid materials like crystals. What happens? The energy levels merge into merge into themselves, and they form a continuous bands. Okay, they form a continuous bands now, which is said to be as energy band rather than energy level. We say it as energy band. So these are such energy bands. It can have energy band number 1, 2, okay, 3. There can be so many bands, energy bands. Okay, there can be so many energy bands like this. So we can say each energy level splits into billions of closely spaced levels, forming what we call as energy bands. So now understanding the energy bands in detail. Understanding energy bands. Now we shall take the example of silicon. Okay, the electronic configuration of silicon. So let's talk about the atomic number. What is the atomic number of silicon? Right, it's 14, right? So what will be the electronic configuration? It would be 1s2, 2s2, okay, 2p6, 6 and 10, then 3s2 and 3p2. Okay, so this is the electronic configuration of silicon. So this means, you see, the inner shells here, the inner shells 1s or 2s and 2p, they are completely filled. They completely filled. S with 2, S with 2, okay, p with 6, 1 2. Next, the outermost shell, that is 3, okay, where n is equal to 3 is the outermost shell here. So it will have 4 valence electrons. 4 valence electrons, 2 in 3s and 2 in 3p, right? 2 in 3s and 2 in 3p. So these valence electrons are very important, we can say they are crucial, because they determine how silicon bonds and how silicon can bond, okay, and how it behaves uh, electrically, how can it give the electricity, how can it conduct the electricity, okay. So like in a single atom, the 3s and 3p orbitals are discrete energy, it will have a discrete energy levels, single energy levels, right? But we consider the silicon substance contains such 100 silicon atoms, right? Not only one atom, there will be 100 silicon atoms in silicon substance. So each silicon atom in that substance has various energy levels, like K shell, L shell, M shell, okay, L shell, M shell. So the energy of K shell of 100 silicon atoms will be different from each other because of the location and everything, and differing in extremely small amounts of energy which are very close to each other. So let us suppose here we are having a single isolated atom. So this will be the first energy level, this will be the second energy level, third energy level, and so on, right? But what about the silicon atom, which is having hundreds of silicon? Now let us take the example of silicon substance, which has 100 silicon atoms as such. The energy levels from different silicon atoms will merge. Okay, the different levels from each silicon atom will merge and form energy bands, right? They form energy bands like this. They form energy bands. It's a first band, second band, third band, so on, right? I hope you understood, right? So in a single atom, 3s and 3p orbitals are having discrete energy levels. But when there can be billions of silicon atoms, they are bound together in a substance or in a crystal lattice, then 3s 3p orbitals of all the atoms will overlap. They like overlap each other, and their energy levels will be splitting into some billions of closely spaced bands like things. Okay, they merge into one another, and they form the what we call as continuous energy bands. Okay, in such a way we get some bands named as valence band, conduction band, and there will be a forbidden gap in between them. There will be so many bands. Mainly we are taking valence band, conduction band, and we are taking the gap between them, which is called as forbidden gap. Okay, we'll see the detailed explanation of it now. We'll take the example of silicon only so that you will understand it easily. First, let me draw energy band diagram. So this is energy band diagram. Okay, let this be valence band, and here is a conduction band. Okay, here is the conduction, and this gap, there is a gap between this valence band and conduction band, which is called as forbidden gap or forbidden energy gap. Okay, forbidden energy gap. Now see this valence band, in the valence band the electrons in the like inner shell, this is the inner shell of the atom, they are strongly bound to the nucleus. They will be strongly bound to the nucleus. So the electrons in the outermost shell of the atom, here in this band, the electrons are called as valence electrons. The electrons in the valence band are called as valence electrons. So this valence band, it contains the outermost electrons from an atom. So these electrons are not strongly bound to the nucleus. So the energy band formed due to these valence electrons is called as valence band. Okay. Generally the valence band has the electrons of highest energy, and the valence band can have it can completely be filled, or it can be partially filled. Okay, half filled. It can be completely filled, or it can be partially filled with valence electrons. So when we take the example of silicon, the 3s and 3p electrons were there, no? So they are the outermost, we can say they are the outermost electrons. They are in the valence band now. So this band can be completely or half filled. So electrons here are bound to atoms. They cannot move freely. Example, in silicon, the valence band is filled with 4 electrons per atom. Right? Now coming to the conduction band, the energy band formed from the outermost energy levels of atom in which there are no electrons present. That is called as conduction band. Okay. The higher energies, they possess higher energies for free electrons. The valence electrons are loosely attached to the nucleus. Even at the room temperature, some of the valence electrons move from valence band to the conduction band. So these electrons which move from valence band to conduction band are called as free electrons. Okay, they are called as free electrons. So these free electrons that are in the conduction band are now responsible for electrical conduction. So the conduction band is generally empty, so it accepts electrons from the valence band. Understood? The electrons in this band are free to move, so that is why they conduct electricity. When we take the example of silicon, the conduction band is initially, when we at 0 Kelvin temperature, it is empty. Okay, but when we apply some external force, like when we give the energy, when we increase the temperature, when we give such external force, electrons can jump from valence band to conduction band as they get the enough energy. Okay, and then they start to conduct electricity. Now coming to forbidden energy gap, this gap, it is called as forbidden energy gap, or simply band gap, you can say. Band gap, right? So the difference, the energy difference between the valence band and conduction band is said as band gap. So electrons will not be here, they cannot exist in this region. They cannot exist in this region. And this band is like at room temperature. For example, when we take the example of silicon, the band gap of silicon is 1.1 electron volt approximately. But it is however, it is very small that electron can jump across that gap when we give some external energy like thermal energy, or when we increase the voltage, okay, as such things, or when we dope also with some impurities. Okay, when we are doping also, when we do doping also, it can jump from valence band to conduction band to conduct electricity. Now what is doping, we'll learn further. Now I hope you understood about the conduction band, valence band, and forbidden energy gap or band gap, right? So what is a valence band? Once we check, the highest energy band that contains electrons at absolute zero temperature also. These are the outermost electrons of atoms, right? These are the outermost electrons of the atoms. They are not strongly bound to the nucleus. And the electrons in that band form the valence band. Okay, valence electrons form the valence band. Next, coming to conduction band, is the next higher energy band where electrons are free to move. Okay, where first of all it is empty. The electrons then can jump from valence band to conduction band, and such electrons are called as free electrons. They are free to move now, and when they are free to move, that means they are conducting electricity. And next comes forbidden energy gap, the energy difference between the valence band and conduction band. So that difference or that gap is called as energy gap, forbidden energy gap. So we can say that electrons will not exist in this region. Now coming to the classification of what is insulator, semiconductor and conductors, mainly this classification is due to the forbidden energy gap. Okay, A material can be said as insulator or semiconductor or conductor based on the gap, based on that band gap. Okay. Now, if the the gap is very small, if there is no gap at all, then it is said to be as conductor. That material is said to be as conductor. If the gap is there, a little gap is there, then it is semiconductor. If the gap, if that energy band gap is very wide, we can say, if it is very wide gap, large band gap, then it is an insulator. Okay, like more than 3 electron volts, then it is an insulator. It will not conduct electricity. The valence electrons will not jump from the valence band to the conduction band. They cannot move. Even when we apply the external force, whatever external forces we apply, even then it cannot jump from the valence band to the conduction band in case of insulators. It can jump in case of semiconductors. There is no gap at all in the conductor's case, right? Like silicon's, as I said, semiconductor, silicon can be the forbidden energy gap or the band gap can be of approximately 1.1 electron volts, right? Not too small to behave like a conductor, or not too large to behave like an inductor. That's why it stands special. Semiconductors stand special, and that is why we are reading the semiconductors in our electronics. That is why silicon became the silicon, or whatever the semiconductors, they became the foundation of modern electronics, we can say. Right? Conductors will have band gap 0. Semiconductors will have little band gap, like less than 3 electron volts, and insulator will have gap more than 3 electron volts. Okay, the best, can you give the examples for insulators, semiconductors and conductors? For conductors, we can take the example like copper, okay, aluminium. These are the example. They are very they have very excellent conductivity, because electrons can move freely because of no energy, no band gap. Electrons can move freely. They'll conduct electricity in a very excellent way. Semiconductors examples are like silicon and germanium. This can be taken as semiconductors. As I said, the band gaps will be 1 to 3 electron volts, between 1 to 3 electron volts. So conductivity is there, but conductivity is there only when we give some external forces, like when we increase the temperature or when we do doping, as such. Now insulators, the band gap is more than 3 electron volts. The band gap here is very large. So obviously electrons cannot move from valence band to conduction band. So no conductivity is there. Very poor conductivity. Examples are like you can take rubber, okay, glass, wood, okay, insulators example. They cannot conduct the electricity. Okay, moving ahead. I hope you understood. So these are the energy band diagrams. You can see band gap is more. So what is this? This is an insulator. Band gap is there, a little bit of band gap is there. So that is a semiconductor. No band gap is there. Band gap is 0. So that is a conductor. Okay, that is a conductor metal. So this is a valence band, this is a conduction band. Right. So we can say energy gap. The size of the energy gap determines the material, whether it is an insulator or semiconductor or conductor. Okay, and it also shows the electrical properties. Based on the material, it will have the different electrical properties. So as I said, for an electron to conduct electricity, it must jump from the valence band to the conduction band. That is why band gap energy determines how easy or how difficult to jump. If there is a large gap, it cannot jump. If there is a small gap, it can jump by some external force applied. Okay, if there is no gap, then it can jump and it can conduct the electricity very excellently. Okay, now classification of solids. As we discussed, there are three types classified as metals can be classified into three types: conductors, semiconductors, and insulator. You can see the difference. Band gap is 0, band gap is less, between 1 to 3 electron volts for semiconductors and more than 3 electron volts for insulators. Examples as I have given, you can see the examples here. Next, behavior. Electrons are free to move, so they conduct electricity. Conductors can conduct electricity. They can conduct semiconductors. They can conduct electricity, but by increasing the temperature or by doping, etc. In insulators, whatever we give, whatever we apply the external force, the electrons will not have the ability to jump. So they are poor conductors, poor conductivity. Okay, comparing the band structures. Similar way, conductors have valence band, conduction bands overlapping. Semiconductors have small or jumpable gap. Insulators have large, okay, a big amount of gap. I mean, insulators, yes, insulators will have a big amount of gap so that electrons may not jump. Coming to the real world applications, conductors, they are used in wiring. Okay, used in wiring, like copper wires we use, no, we use copper wires to carry the electricity efficiently. Okay, and the example for semiconductors can be used in electronics, like silicon chip power computers by controlling electron flow through the small band gap. Coming to insulators, they can be used for safety purposes. Okay, as they do not conduct electricity, they can be used for safety purposes, like to avoid the conduction we are using insulators. Rubber, plastic, it can protect us from because there is a large band gap and it prevents the electron flow, it prevents the electricity, so we can use the insulators for safety purposes, right? So these are the applications for conductors, semiconductors, and insulators. Now we came to the end of the session. We will practice some questions. You try to answer these questions so that you will understand that whether you understood this topic or whether you understood this concept or not. Okay, so let's practice some questions. Here the first question says, in the single atom energy, like according to Bohr's model, you have seen Bohr's model, right, in our earlier classes, Bohr's atomic model. Okay, it can have an electron. In Bohr's model, there is an electron that exists between two energy levels. It is asking, according to Bohr's model, can an electron exist between two energy levels? Can an electron exist between two energy levels? Okay, suppose there is n is equal to 1, 2 energy levels. Okay, so can electron exist here? It's asking the question that can electron exist here? If yes, why? If no, why not? Why? So think of the answer. Just think whether the electron can exist between those two levels. Yes or no? Obviously no. Okay, electrons cannot exist between two energy levels because these energy levels are quantized like steps, as I gave the examples. Okay, energy levels are quantized, means they can only occupy some fixed specified orbits only with some defined energies only. Okay, by moving in between these levels, they must absorb or they must release some quantum of energy, some specific quantum of energy, but they will not exist, electron cannot exist between two energy levels. Understood the answer? Next question, band formation. What happens to discrete energy levels when billions of atoms come together to form a solid? Okay, this question relates to the explanation we had now. Okay, what happens to the discrete energy levels when you have some discrete energy levels like this, no? Energy levels, n is equal to 1, 2, 3, 4, 5, 6 energy levels. Now he is asking the question that what happens to these levels when there are not 2 or 3 atoms, but when there are billions of atoms. Okay, so let us take as per 23 atoms in a solid, in a substance. Okay, then what happens to these energy levels? The question is, what happens to these discrete energy levels when billions of atoms come together to form a solid? What happens? Can you think of the answer? Are you getting the answer? The discrete energy levels will split into billions of closely spaced levels. Okay, they'll split into billions, like this. They'll split into billions of levels due to many atomic interactions. Then these levels will merge into a continuous energy band. They form a continuous energy bands, right? They'll form a what we call conduction band, valence band, etc. Understood how the band formation is occurring? By the splitting of energy levels, bands are forming. Okay, now next question, what is band gap comparison? Means he's asking us to arrange the following in order of increasing band gap. Okay, right. As I said, we are having 3 classifications of materials: conductors, insulators, and semiconductors. As we discussed earlier, a material can be classified as conductor or insulator or semiconductor based on the band gap, right? If the band gap is very large, then it is an insulator. If the band gap is in between the conductor and insulator, that means if the band gap is little so that the electrons can jump to conduction band, then we can say that the material is semiconductor. And if there is no band gap at all, then it is a conductor, right? So we have arranged, let us arrange. For conductors, what will be the band gap? Band gap is 0. For semiconductors, the band gap can be in between, like 1 electron volts to between 1 electron volt to 3 electron volt approx. And for insulators, the band gap can be more than 3 electrons, right? This is the increasing band gaps of conductors, semiconductors, and insulators. Increasing order of the band gap that decides the material is conductor or semiconductor or insulator. Right, next question. It's about electrical conductivity. It's asking, why does a semiconductor, little, 1 second. Why does a semiconductor's conductivity increase with the temperature while a conductor's conductivity decreases? Okay, interesting question, right? Okay, you understand the question, no? It's asking when we are giving more, when we increase the temperature of the semiconductor, the conductivity will increase because the electrons will jump from the valence band to conduction band with the increase in temperature, and the semiconductors will conduct properly. But when we increase the temperature of a conductor, the conductivity will decrease. Why? Yes, because see here, semiconductor, as the temperature is rising in semiconductors, electrons, what will they'll gain enough energy, right? They'll gain enough energy to jump beyond the band gap and they'll start conducting. Okay, this is understandable. Now what about in conductors? What happens in conductor is, when the temperature is high, when the temperature is increased, the collision between those electrons or the collision between those atoms will resist the conductivity. Okay, such collisions between electrons and atoms will resist the conductivity, therefore the conductivity will be reduced. Understood? Next question, the last question. It's about material selection. So it's asking, if you need to design a material that prevents electric shock, okay, if you want to prevent the electric shock, what would you choose? Would you choose a material with a small band gap or large band gap? Okay, justify your answer. So simple, right? To prevent the electricity, to prevent the conductivity, what we will choose? Obviously, we'll choose a material whose band gap is larger. That means we'll choose an insulator, right? Insulator means it will have a band gap, very wide band gap it will have. So we will choose a material with a large band gap like an insulator, because a large band gap will prevent the electron from jumping from valence band to the conduction band. So it ensures the conductivity is not there. It ensures no conductivity is there. So this will make us prevent the electricity. So we can use a rubber or plastic. Okay, they are the ideal for insulator and for safety. So we'll use insulators whose band gap is large. Right? Understood? So that's it for today. I hope you understood the session. I hope you could you answered these questions. Okay. I hope you enjoyed the video. We'll meet in the next video, and there we'll study about the classification of solids, mainly about semiconductors, right? Bands, how the bands in semiconductors are formed, what are the semiconductors, all those we'll learn in the next video. Thank you.